Okay, so in the last video we talked about how to calculate the electric field strength due to a single point charge. And remember the equation that allows us to do that we derived in the last video is E equals K big Q over R squared, where Q is the charge which is creating the electric field. And so that equation allows you to calculate the electric field for a single point charge. Generally speaking, if you have a more complicated distribution of charge, let's say you have like a bajillion charges all spread out over like some solid object, then generally speaking you would need to do some type of integral. You would have to use integral calculus to be able to find the electric field due to that charge distribution, because again this equation only works for a single point charge, and if you had like a bajillion point charges all like thrown onto an object, then you would have to add up each of those electric field contributions individually. But there are some relatively basic charge distributions that you need to be aware of that actually have simplified electric fields, and the most common one that you see is the electric field created between two parallel plates of metal that have an equal and opposite charge. And so usually this is drawn like you can see here in the bottom left. But the situation is you take two metal plates and you somehow make the top charge positive and you make the bottom charge negative. Okay, now it's not important why this happens, and the explanation is kind of complicated to explain without calculus. But basically, if you have this type of charge distribution with two parallel metal plates, then you get an electric field that is uniform between the plates. Okay, and when I say uniform, I mean constant. And so this is a very common type of situation to see in IB problems, because now you have a situation with a constant electric field. And in real life, you typically have situations with changing electric field, and there's a lot of calculus involved. And so one of the ways you can do simplified problems, like you do in IB physics or in high school physics in general, is by having a constant electric field. And so the electric field due to a point charge is not constant because it depends on distance. The farther you get from the charge, the weaker the electric field gets. But if something is special about this distribution of charge, where if you have the two parallel metal plates and one is charged positive and the other is negative, you get a constant electric field between the two plates. Now, make sure that you understand what the electric field looks like in this situation, because there have been IB problems in the past that ask you to sketch the electric field for the situation. And basically what the field looks like is, if you look at the bottom left down here, you can see that for the most part these arrows are showing the direction of the electric field. It's kind of hard to see maybe, but these are all arrows pointing down, and you can tell based off of how they're uniformly spaced that the electric field is uniform everywhere in between the plates. Okay, so that means if I measure the electric field here or here or here or here, I would get the same magnitude of the electric field at all those points in space. Okay, now there is one exception to that. Notice that at the edge you have what's called edge effects. I kind of think of this situation as like an electric field sandwich, where at the ends the electric field starts to spill out. If you imagine like an ice cream sandwich, eating an ice cream sandwich, like for the most part in between the two parts of cookie, everything is nice and uniform, but if you bite into it, it squirts out at the end. And so at the edges, the electric field starts to spill out with this kind of charge distribution. And you would never be able, or you would never be asked to do calculations at the edge because the electric field stops being uniform there. But you might be expected to know what the electric field looks like at the edge. Okay, so typically if you're doing a problem with this situation, they would usually give you the electric field inside. You could not calculate it because, again, the equation we have for electric field only works for a point charge. And so you would not be able to calculate the electric field in here with an equation that would typically be given to you. Okay, so let's see. I do want to do some basic problems with this type of charge distribution though. So here is an example. It says the uniform electric field strength inside the parallel plates is 275 newtons per coulomb. A positive 12 microcoulomb charge having a mass of 0.25 grams is placed in the field at A and released. Okay, now remember that electric field lines always run from positive to negative, and the electric field also points in the direction that a positive charge would feel a force. So looking at the picture, if we have a positive charge at A and the electric field lines are pointing up, we can infer that the positive charge is going to experience a force up due to the electric field. Okay, now we can calculate the force on that particle, the 12 microcoulomb charge, by using the definition of the electric field, and by definition, the electric field is the electric force per unit charge. And so if we know E, which is the electric field strength, and we know Q, which in this case is 12 microcoulomb, that's the charge, that's Q, this is E, then we can very easily calculate the electric force just by multiplying Q by E. And that's what you see down here, this calculation. And B says, what is the weight of the charge? And of course, we know how to calculate force of gravity, which is the same thing as weight. We're given the mass in grams, and so you would have to convert that to kilograms. And again, you can see how the work looks right here. That both of those calculations are very basic type of calculations. And it's also possible to adjust the electric field so that this object actually floats. And historically speaking, that's the basis of what's called the Millikan oil drop experiment, which is basically, in really simple terms, I don't want to sell it short because it was a really interesting experiment, but basically the experiment was able to find the value for the elementary charge, the 1.6 times 10 to the negative 19 coulomb. And basically what they did, again in simple terms, is they sprayed, they took oil and they sprayed it in between two parallel plates, and the oil particles, the droplets were charged, and really thin mist drops of oil. And they adjusted the electric field strength until some of the oil droplets floated. In other words, until the force of gravity and the electric force were equal to each other. And by carefully measuring the electric field and the floating oil droplets and doing these calculations and all this crazy math, they were able to come up with an expression for the elementary charge, which again is 1.6 times 10 to the negative 19 coulomb. And I'm really oversimplifying how that works, but it is possible for the net force on a charged particle in this situation to be 0. That's my point. Okay, so moving on to the next part of this example. Given the electric force up and the force of gravity down, okay, I could also tie this into a Newton's second law problem. So here we see part C says, what is the acceleration of the charge? And so if we want to find acceleration, then we can just use Newton's second law, F net equals ma. And we know we have, the electric force going up and the force of gravity going down. And so the net force would just be the sum of those two forces. Okay, and so here you can see the work is basically pretty straightforward, calculating the net force, and if you plug that in to F net equals ma, then you can find the acceleration. Okay, and so that's just a really basic type of situation involving the electric field between two parallel plates. The reason we can do this type of simplified problem again is because in this situation the electric field is uniform. Going back to part A where it said what is the electric force acting on the charge, generally speaking the electric field is not constant in a given situation. So as the charge moves, the charge is moving because there's a force on it. As the charged particle moves, the force also changes. And then because the force changes, the acceleration changes. And so it moves faster this way or that way, and that makes the electric field change. And it becomes a whole big mess, and calculus is involved. But because the electric field in this type of charge distribution between two parallel metal plates is uniform, it's the basis for a lot of problems in this unit. Okay, and the last thing I want to say about electric fields before we finally move on. Path electric fields is just what is on this slide. Okay, again, without any proof, I will tell you it is an experimental fact that stationary charge cannot exist inside of a conductor. Meaning if you take a conductor and you try to put charge in it, the charge is going to go to the outside of the conductor. Okay, it cannot exist inside of a conductor if it's stationary. And basically the reason for that is if you had charge inside a conductor, there would be an electric field, and that electric field would move, or would put a force on the free electrons in the conductor, and then the free electrons would move, and basically everything would keep moving and push and push and push on each other until all the charge ends up on the outside. Okay, so because conductors have those free electrons that we talked about before, you cannot put stationary charge inside of a conductor. So any charge on a conductor is going to be distributed along the outside of that conductor. Now, in the case of a conducting sphere, because a sphere is symmetrical, that charge is going to be uniformly distributed. Meaning, if you throw charge onto a conducting sphere, it's going to be evenly spread out over the sphere. And by the way, this is normally where I would do an awesome demonstration using the Van de Graaff generator at school, which unfortunately I cannot do, but at some point I might try to record a video and show you guys how that works, because it's kind of interesting. But if you've ever seen it in my classroom, I keep it like back in the lab, and it's like this metal dome thing, and that would be an example of like a conducting sphere, because it's a metal sphere. Now, this bullet point right here, again, I state this without proof. Just take my word for it. If this was like an AP calculus class, I would, maybe explain that a little bit more, but it's not important that you know the why behind this. So just believe me when I say this. It can be shown mathematically, and I'm not going to explain what the math behind that is, that because there's no charge inside a conductor, no stationary charge, the electric field inside a conductor is always 0. Okay, as long as you're talking about stationary charges, the electric field inside a conductor is always 0. Now I say stationary charges because you can force there to be an electric field inside a conductor. I mean, that's how circuits work. Like you can hook a battery up to a metal wire, and you can force there to be an electric field inside a conductor. But if you're talking about stationary charge, non-moving charge, it can't be done. Okay? And again, the reason for that is because there's no charge inside a conductor, the electric field inside a conductor is always 0. I say that without proof. You don't need to know why that is, but it is true. Okay. So meaning if you take a metal sphere and you put charge on it, all the charge is going to go to the outside, number 1. And number 2, the electric field inside the sphere is always going to be 0. And that's just a fact that you just need to know. Okay, so for example, this is an example taken from an IB question, I don't know, 4 or 5 years ago. It's an older question, but it's still under the current curriculum. But this question said, an isolated metal sphere is placed in a vacuum. The sphere has a charge of magnitude 12 nanocoulomb. Outside the sphere, the electric field strength is equivalent to that of a point negative charge of magnitude 12 nanocoulomb placed at the center of the sphere. The radius of the sphere is 25 millimeters. Okay, this bit right here is also something important that you want to add to your notes, because it's another interesting property of electrostatics. If you have a conducting sphere, the electric field inside of the sphere is 0. There's no charge inside of the sphere. But because of the magic of mathematics and calculus, if you pretend like there's a point charge in the middle of the sphere, then the equation for a point charge, E equals kq over r squared, that equation works outside of the sphere. Even though there's no charge inside the sphere, in other words, let's say this is a conducting sphere, all the charge on the is on the outside. There is no charge on the inside, but through the magic of, like, I don't know, mathematics and calculus and whatever, this equation works, the kq over r squared equation works outside of the sphere by pretending that all of the charge that's out here is actually all focused at the center. Okay? So in other words, if you pretend that all the charge, that big Q that's spread out over the surface of the sphere, if you pretend it's all located at the center, even though it's not, of course, then this equation, the kq over r squared equation, works outside of the sphere. It doesn't work inside the sphere because the E field inside the sphere is 0. And again, I say that without proof. That's kind of like a calculus-y thing. But the year they gave this question on the IB exam, the first part was, on the axes, draw a graph to show the variation of the electric field strength with distance from the center of the sphere. Okay, and so here's how this works. The electric field strength inside the sphere is 0. Okay, that's just a fact that you have to accept. What that means is that if you're starting at the center of the sphere and you're going out from the center up to 25 millimeters, because that's the radius, the electric field strength would be 0. And so you would just draw this graph to here. Now, once you get outside of the sphere, this equation magically takes over instantaneously. All of a sudden, it's like, wow, there's a point charge at the center of the conducting sphere. There's not, but the equation works as though there was. Meaning, you get the correct answers, playing make-believe, even though that's not actually correct. And so, as soon as you get outside the sphere, the electric field is going to jump up. Now, what is it going to jump up to? Well, let's find out. If we use the equation kq over r squared, we have k is 9 times 10 to the 9. Big Q is 12 nanocoulomb, so 12 times 10 to the negative 9 coulomb. And once we get to the outside of the sphere, where this equation applies, we are a distance of 25 millimeters from the center. Okay, and so that means for r, I should do 25 times 10 to the negative 3, because I have to convert from millimeters to meters, squared. And so I'm going to put this into my calculator and see what I come up with. And this value I'm calculating is going to be the electric field strength at the surface of the sphere. Okay, so I'm typing this into my calculator. I forgot to hit divide, so that's cool. Alright, and so the answer I get is about 172,800 newtons per coulomb. Alright, notice that the units on the y-axis are times 10 to the 5 newtons per coulomb. So this is, between 1 and 2 times 10 to the 5, probably closer to 2. So probably, I don't know, here somewhere. So here's what's going to happen. The second you get to the surface of the sphere, the electric field is going to jump up. There's literally a jump. In mathematics, you call this a jump discontinuity, because this function is not continuous. And then all of a sudden, it's like there's a point charge there's a point charge at the center of the sphere. And what happens as you get farther from a point charge? It decreases. Okay, because there's an inverse square law. Distance is being squared on the bottom, and so this is going to decrease like this. A lot of people would call that decrease exponentially, but it's not technically an exponential. It's technically an inverse square. It's not quite the same. Okay, but that's basically what this graph would look like. And some people think it's weird that the electric field is not continuous here, and it kind of is weird, actually, but that's how it goes. Okay, so pause it there. Make sure you have that added to your notes. Okay, so I'm going to erase this. And I'm just going to kind of click through these slides. Most of these examples are worked out so you can see what they look like on your own. So you should be able to understand them without any explanation by me. They're mainly similar to the problem that we just saw. Okay, so I'm going to the next slide. And you can look at the answers to the questions down here. Okay, here's the question. The answer is down here. And by the way, somebody probably is going to point out the fact that there's not a negative sign here in front of the charge, even though it's an electron. They're leaving out the negative sign because I've said this before. The negative sign on the charge does nothing for direction of the force. Okay, but if you put an electron on the outside of this negatively charged sphere, the force is going to be repulsive. Okay, so they don't bother putting the negative in front of the 1.6 times 10 to the negative 19, even though it is technically a negative charge, because all they're really interested in is the magnitude. Okay, and this number down here, that's the mass of the electron. That would be given to you, of course. Okay. Okay. Just to show you one more example, which of the following graphs could represent the electric field inside a conducting sphere of radius r as a function of the distance from the center of the sphere? Okay, well, clearly the answer is V because we literally just saw that a few minutes ago. This is actually taken from an AP physics exam a couple years back. Sometimes they ask similar types of questions to IB exams. But yeah, so pretty straightforward stuff. All right. There's only one more key concept left in this unit, and that has to do with potential difference. So I will save that for another time. What I want you to do now, though, is I want you to check out this video I'm going to link. It's a good video to tie everything together and maybe explain some things in a different way and really just reinforce everything we've been talking about as far as the electric fields go, because it's kind of like abstract in a way. Okay, so please check out that video, and I'll ask you some questions about that video in just a second. Okay, as always, please let me know if you have any questions, and I'll see you guys in the next video.